Hello and welcome to another live stream from Test Oil. This one is on the topic of why aren't my oil analysis results correlating. I'm your host, Evan Zabowski. I am the Senior Technical Advisor here at Test Oil. And just so we're clear on the topic, why are they not correlating, we're not here to discuss why your results may not correlate with reality, meaning that sometimes your results look better or worse than what you think you're experiencing in the machines. That is probably directly related to sampling procedures or even the location. What we're going to talk about today is why certain results don't seem to correlate with each other. And I have three different examples that I'll give you, and all of these will use excerpts from our lubricant analysis section of the comprehensive class to explain why the results do not correlate. Now, the simple answer to all of these is, generally speaking, they're maybe not meant to correlate. And the logic is quite simple, that if you did two different tests that always directly correlated with each other, meaning that as long as one was high, the other one was high, or whichever direction they're going to go, there wouldn't be a lot of point doing both tests. So each test is meant to test something specific or see it from a specific viewpoint. So that's mostly what we'll be seeing here. So without further ado, here's our first example. Let me discuss why your wear metal results and maybe even your silicon levels in your elemental spectroscopy don't necessarily correlate with your particle count or vice versa. Now, as I said, I'll be pulling materials from our lubricant analysis section, and in this section, one of the things we go over is scope and significance of certain tests, and then we describe how the test is performed so you can see why it's able to come up with the result that it does. The first test that I'll discuss is elemental spectroscopy, and the scope and significance of this test is it's meant to measure wear metals, additives, and contaminants. So it's one of the most well-rounded tests that we can perform in terms of covering a broad scope of measurements. Now, the basic principle of this test is that your sample is diluted with a solvent and then is turned into an aerosol and injected into a plasma. When the sample reaches the plasma, some of the electrons in it are excited, or what we would say is ionized, and then those ionizations cause those electrons to move up a state, and when they return to the original lower state, they give off light. This light is what we measure, and this light is a unique spectrum, a unique color of light for every single element on the periodic table. Hence, that's why it's called elemental spectroscopy. This test does not measure for compounds, chemicals, or alloys. It measures the elements that go into the compounds, the chemicals, or the alloys. So as a quick example, if this test was to see Babbitt wear, it wouldn't come back and tell us that you had Babbitt in your oil. It would say that you had lead and tin. As well, if you had bronze wear or brass wear, it wouldn't tell us you had either brass or bronze. It would tell us again that you had lead and tin with some copper. So it's up to the interpretation of the ratios or proportionalities of certain elements to each other that we can determine the likeliest sources. So just to stress again, it's called elemental spectroscopy because it's measuring the elements only. And just to give you a little preview of what the instrument actually sees, it sees these unique bandwidths of light, different colors within the visible spectrum, and every element, like I said, has at least one unique bandwidth that we can focus on to identify it from other similar looking metals. Now, with this test, and this is the important part of why it doesn't correlate, is that this test is primarily focused on particles within the 0 to 5 micron range. Those are the ones that are measured most accurately by this instrument. Elements that appear as particles within 5 to 10 microns are measured at a significantly lower accuracy. And anything much above 10 microns doesn't even really enter the equation here because it's not being present in the plasma. Now, with that said, a lot of people concern themselves that that doesn't seem to be measuring much. Well, the point is that additives, as an example, are submicron, so they're definitely within the 0 to 1 micron range. And normal wear particles and normal contaminants that you should be concerned about are going to be clearance-sized particles. And most dynamic clearances in most types of contacts under lubrication are under 5 microns. So This covers a lot of what you expect to find under normal conditions. It's when things go abnormal, when things get severe, that perhaps this test actually does not capture everything you're hoping it should. But again, that is the intent of this test, is to measure what we expect to find most of the time. Now, a quick comment here about interferences. Sometimes this is why your results don't correlate. With this test, because we have to dissolve your sample with a solvent, what if it doesn't dissolve? If what you send us is not a normal hydrocarbon-based oil, there may be the possibility it will not mix well with our solvent and therefore may not turn into an aerosol properly to be introduced into the instrument. There are, of course, ways to overcome this, but in general, that may lead to lower accuracy in the numbers because, again, our calibration is set up expecting a certain type of solvency to the sample. Now, as just a quick visual reference here, just so we make sure this is clear, again, this test measures particles generally within 0 to 10 microns. It just measures the ones between 0 and 5 microns most accurately. It does not necessarily measure the ones between 5 and 10 microns with much accuracy. Luckily, though, there's a bit of a handshake here where we can hand off the results to a different test, and those results would give us an insight into particles that are larger than 5 microns. So again, just making sure we're clear, what is the intent of the test? Because that sometimes tells you exactly why the two results will not correlate. Now, if we move along to particle counting and speak about optical particle counting first, because that's the one most common to people, optical particle counting is meant to measure contaminants by and large, and it may measure wear particles as well after they've been generated by the contaminants. But the whole scope of particle counting is to measure the buildup of solid material in the oil, solids being, of course, considered to be very detrimental to the life of the oil and to the life of the machine. Significance of these results is generally the higher the particle count is due to contamination will drive a higher particle count due to wear. Now, the basic principle of this test, optical particle counting, is done by taking your sample and flowing it. So it's a moving sample past an intense source of light, which is why some people call this laser particle counting. And what happens is as the stream of oil goes through the beam of light, any particles that are found within the oil will cast a shadow on the CCD detector. Basically, it's like the imaging device in a digital camera. What this instrument then does is sizes and counts those shadows. One of the lesser known details about how it sizes and counts the shadows, though, is that it is not measuring the longest side, the shortest side, or even the average length of any of the sides of these shadows. It does something rather unique called spherical equivalency, which is all about the area of the shadows. So if you take an example like this and imagine a 10 by 1 micron particle casting a shadow as it goes through that stream of oil passing by the intense source of light, it would cast a 10 square micron shadow. So that's easy math to understand. The harder math, though, is when it does this thing called spherical equivalency. It assumes the particle is a sphere, and a sphere would cast a circular shadow. So what it has to calculate then is the diameter of that circle that would have the same area. So to save yourself too much time on that math, it works out to 3.6 microns. And the interesting thing about that particle is a 10 by 1 micron particle would be actually quite concerning to most people monitoring their systems, but the instrument doesn't report any particles deemed smaller than 4 microns. So that particle actually goes unreported. So as you can see right away, the correlation between elemental spectroscopy measuring most accurately particles under 5 microns and this test reporting particles greater than 4 microns, which in effect are really actually kind of larger than 4 microns, already shows you that you should not expect much of a correlation between these two sets of results unless you've got a broad range of particle sizes. Now, just to finish off particle counting here, though, the limitation to a particle count, as I already said, is it doesn't report anything smaller than 4 microns, but it really can't report anything much larger than about 100 microns. And that has a lot to do with the film thickness of the oil going through the light source and detector arrangement. Interferences, though, here's the key. With optical particle counting, because it is sizing and counting shadows, anything else that has the ability to cast a shadow could potentially be counted as a particle when in fact it actually isn't. And these tend to be things like air bubbles, water molecules, and even soft contaminants like the oxidation byproducts that lead to varnish. So that's why at test oil we prefer to use pore blockage particle counting. Pore blockage particle counting uses a completely different premise to get the particle count done. What it does is uses a calibrated screen, which are either 5, 10, or 15 micron holes in them, and it pushes the oil through the screen at a constant pressure. The actual measurement is of the decay of flow on the opposite side of the screen. Now the neat thing with this test is that by the particles starting to plug up the screen and the flow starting to decay, we can extrapolate all the results from one screen into the broad range particle count that you're used to seeing. Some studies have shown that the accuracy of this test has about 1/4 the error that optical particle counting has, which right away should give you insight as to why we prefer to choose pore blockage particle counting over optical particle counting. But here's a bigger reason. The limitation to this test is the same. It still doesn't report particles under 4 microns, but the other issue is that it has no known interferences. Air bubbles, water molecules, and any oxidation byproducts have no impact on this test, which means we can run this test without any special preparation to the sample, which would be required for optical particle counting. And the issue that some people would have with any preparation required for optical particle counting is it could start to skew the numbers away from reality. Among the many ways we have of removing the impact of air bubbles, water molecules, and soft contaminants is to dilute the sample and then either sonicate it or vacuum it or both. And sometimes what this does is break up larger particles into smaller particles, thereby skewing your results. So not only is pore blockage more accurate than optical particle counting, it has, like I said, less preparation required. So it's a bit speedier for us to do it. But in the end, hopefully now you understand why you don't always expect elemental spectroscopy results to correlate with a particle count. They simply are not measuring or meant to measure the same size of particles. So like I said, unless you have a broad range of particle sizes, you may not see both sets of results go up or go down at the same time. Now, moving on to our next example, some people ask a slightly different question related to degradation. And they wonder why acid number results don't always correlate with ruler results. Well, again, starting with the scope and significance, you can start to understand that we're coming at this from two completely different perspectives about degradation. The scope and significance of acid number is it's meant to measure acidic constituents in the oil. Now, what that means in layman's terms is any acids that build up. Now, to be fair, many oils begin with some acidic additives in them, so there is some measurable amount of acid number in new oil. What we're looking for is the increase over time. That often can be attributed to degradation of the hydrocarbon base oil and some of its additives. Now, how this test is performed, it's a simple titration. If you can remember your high school chemistry classes, you may remember playing with acids and bases. And you may recall that if you put phenolphthalein as an indicator in them, you could make the solution turn from pink to clear to pink again. Well, we kind of do the same thing, except we use naphthylbenzene. And it starts off a very bright orange color. And as the reaction hits a neutral point, we get a dark greenish brown kind of color. So what we do is we treat your sample as if it was an acid and we add base to it. By counting how much base we put in, we can determine how much acid was present. So like I said, very much a simple basic chemistry type reaction. Now, the limitation to this test is that acid number, to be fair, tends to be a bit of a lagging indicator when it comes to very large reservoirs. So if you've got, say, more than 200 gallons of oil, you're going to find your acid number does not react as quickly as some of your other tests, like ruler or even RPVOT. Interferences to this test, though, is water content. High degrees of moisture in your oil not only promote the formation of acids just in service, but can impact formation of acids during testing, meaning sometimes we will report a higher than expected acid number because acids have formed while the test was being run. My simple logic to a worry or concern like that is if your water content is high enough to mess up the results of this test, there's your problem. You have too much water in your oil, and that should be your focus more so than what your acid number doing at this exact moment in time. Now, Some of you may be familiar with a slightly different version of acid number called potentiometric, and that is very, very similar to the version I've just described. Comes up with a very similar result, it just doesn't use a color indicator. But anyways, the other test that I wanted to mention is, of course, ruler, because this is the one people expect it to correlate with. But the issue is that with ruler, the scope and significance is quite a bit different. In this case, what we're trying to measure is the level of antioxidant additive in the oil. And if you think about it right away from that perspective, you realize that the acids from acid number are the byproducts of the degradation. Ruler, just by its overall intent, is meant to measure the antioxidant level. So it's measuring the ability to fight this degradation. So right away, we're seeing basically two sides of the same coin. But we can't always expect that as ruler goes down, acid number will climb, or as acid number has climbed, ruler will go down, and expect to see that that always stays a direct relationship. But the significance to ruler is, yes, as the antioxidant level goes down, you will eventually expect that oil to degrade. But just because you have less antioxidant doesn't mean it is degrading. It just means it doesn't have as much reserve for fighting that degradation. Now, to give you an idea how different this test is in terms of how it's performed, we take your sample and we mix it up with an electrolyte. So if you're thinking in your head Gatorade, you're not too far off. They do come in different colors for different oil types. But once the sample has been mixed with electrolyte, we hit it with a voltage using a technique called linear sweep voltammetry. And what this does is it reacts with those antioxidants. So the output that we get is a voltammogram, which is like the picture you see here. And we will see one or two peaks appearing depending on the type and style of these antioxidant additives. Predominantly, most oils contain either an aminic or a phenolic antioxidant, but some oils do contain both. So when we're looking at these results, what we expect to find is some peak, and we'll measure the height or area of this peak. And as we test used samples, we will compare those results to the original new oil peak and report it as a percentage. So this is a number that should begin at 100% and trend downwards towards 0. Acid number, on the other hand, starts at some baseline value and climbs upwards. Now, in terms of limitations to this test, we do need that new oil reference. If we have not seen your oil before, we don't have a way of actually reporting this percentage to you. We'd only have a way of creating a voltammogram, which wouldn't tell you much. But in terms of interferences, one of the things that can really throw off a ruler test is if there's ever a mixture of two oils. If you ever accidentally top up with the wrong oil, or you just simply stop buying from one supplier and start buying from another supplier, that can mess up how these results are interpreted. And if you look at the voltammogram pictured here, it shows two completely different oils with two completely different peak profiles. So acid number is kind of nice in that we can do acid number regardless of having a new oil reference, regardless of mixtures. But on the other hand, ruler is quite definitive at showing us exactly what your oil has in it. So again, you can't expect these two sets of results always to correlate. You may find that your acid number climbs at a slow and steady rate, but your ruler value drops much more rapidly. And the concern will be that at some threshold cutoff, generally very low levels, like around a ruler value of say 20 to 30, you might suddenly see your acid number take off. Because at that point, your oil has very little antioxidants willing to fight the degradation that's occurring. And at that point, you would need to schedule either an oil change or some sweetening. Whereas acid number, you just watch slowly climb steadily, 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 and then all of a sudden there'd be a major inflection, and like I said, it would take off. So you're not going to see quite a direct relationship, or an inverse relationship really is what we're going for here, between the rate at which an acid number climbs versus the rate at which a ruler falls. So it's good to do both. It's good to see it from more than one perspective, but understand that ruler does have a couple limitations to it. Now, my last example, which is in a bit of a different direction here, isn't so much why two sets of results don't really correlate, but why they don't correlate with the expectation. And the two that I'm going to go through are MPC and UC. Membrane patch colorimetry, which some people refer to as the Varnish potential test, and ultracentrifuge, which is another variation of this similar measurement. And the comparison here is, will they correlate with actual varnish? And this is an interesting question, and I've gotten this one quite a few times because people want to monitor for, of course, the potential presence of varnish. And sometimes when they do inspections, they see what doesn't seem to match the sets of results. But again, if I explain how the tests are performed, you'll understand why this correlation doesn't exist. And this one has nothing to do with sampling practices or procedures or location. So MPC, membrane patch calorimetry, the scope of this one is to measure oxidation byproducts, the insolubles as we call them, that build up in your oil. The significance is that the presumption being the higher the level of these insolubles, the more likely they are to plate out and form what we would call varnish. So that's why some people refer to this as the varnish potential test, because they correlate a high MPC value with the potential to create varnish. However, I'll explain how that may not be quite the correct assumption, and we'll tell you why the test is not called varnish potential by most of us in industry. Now, the basic premise for how the test is done is we start with a patch. We take a small piece of membrane filter paper and we run some oil through it. Once we've run the oil through it, we rinse it with a solvent to get rid of any oil residue, and what we're left with is just simply everything that was suspended in the oil. So this would be some solid particulate, of course, but what we're hoping is that it's mostly going to be comprised of all these soft contaminants, these byproducts, these insolubles, whatever name you want to give them. What we then do is we use a very sophisticated, highly specific spectrophotometer to analyze the color of that patch. And if you're wondering what the heck is a spectrophotometer other than the picture that you see there, essentially it's the same technology that goes into a hardware store when they color match your paint. It's just an instrument that very accurately measures color. And in the case of color, you may be familiar that color can be measured on an RGB scale for video or a CMYK scale for print. We use, and I understand the irony here, an LAB scale. And what we're concentrating on is the L value, and that is the darkness of the color. So it's not how vibrant or how persistent the color is. It's not what shade this color are, because you can see we have an A and a B for green to red and yellow to blue. It's how dark that color is, because it's the darkness that tends to indicate the oxidation byproducts. Basically what I'm saying is the blacker it looks, the worse it is. But because we can't necessarily use human eye detection for its subjectivity, we need a way of accurately doing this in a repeatable fashion. So spectrophotometers are used to do this. Now, the nice thing about this test is that it measures what's in the oil very, very accurately. Problem is, varnish may not be in the oil, right? By its very nature, the term varnish means insolubles plated out onto surfaces. So if the varnish is already plated out on the surface, it's certainly not suspended in the oil to show up in a sample. And right there is your first clue as to why the results don't correlate. As for interferences, though, it should be known that since we're mostly focusing on the darkness of that color, anything else that's going to make the oil appear dark can influence the patch. So carbon particles would be the key one there. So any tiny soot particles from microdieseling or any electrostatic spark discharge may skew your MPC values to be a little bit higher than maybe what you would expect. But a completely different approach to measuring these insolubles is called ultracentrifuge. And this is a test that's done by ExxonMobil. And basically what they do is sort of the same approach in that they try to quantify the insolubles in your oil, significance being, again, higher insoluble content, greater tendency to varnish. The method that they use, though, is to simply take your oil, put it in a centrifuge tube, spin it at a ridiculously high speed for half an hour, and when the test is done, you invert the test tube and compare it to this scale that you see here on screen. Basically, if it matches the top row, it's okay. If it matches the bottom row, it's not okay. And it's just a quick and easy way of identifying the level of insolubles or any other suspended matter in your oil. So as for limitations to this one, again, if the varnish is already plated out, it's not going to appear in the oil sample. But as for interferences, this one has a slightly different interference, so much that the energy that goes into this sample as it's being spun has a tendency to heat it up. If the sample heats up, it may hold things in solution better than at a lower temperature. So you have to make sure you maintain a reasonable temperature during this test. On the other hand, if you overcool it, you can force things to basically condense out of the oil faster than they should, and you might skew the results to be higher. But either way, one of the key things I like to point out when we go through all this testing is how to interpret the results. And when I go through the interpretation of results, I do mention what is the most common cause for these numbers to go up or down. And for MPC and UC, that's an easy answer. It's oxidation. And what prompts oxidation is generally, it's a degradation reaction with oxygen. So you do need some contact with oxygen, with an air supply. But what can accelerate it greatly is, of course, heat. But the other thing I like to mention when we talk about interpreting results is not just the most common cause, but what are the exceptions? What are the other things that people don't always think of? And with MPC and UC, I'll show you the exception here. And it's really is the answer to why the results don't correlate. The logic being that when you take a sample, it may or may not have a level of insolubles in it. As that level of insolubles climbs, you expect the potential for varnish to be higher and higher. What many people don't realize is that if they trend this result and the result stays flat, meaning the MPC and the UC results never really change, that could be concerning. Because what it could mean is that the varnish is plating out as fast as it's being generated. So whether the result's high or low, but just saying it's always constant, doesn't necessarily mean you're not creating the insolubles. It just means they're depositing as fast as they're being created. On the other hand, seeing really low MPC, really low UC values, again, doesn't mean that you don't have varnish. It could just mean most of it has actually already plated out and therefore is not suspended in the oil to be collected as a sample and then sent to the lab to show up on the report. The flip side, though, would be what if it's a really high result, right? Many people panic then and think, oh my goodness, I've got tons of varnish in my system. So they drop the oil, they drain it, and they look inside and they don't see any varnish. And the answer is, well, because it was all in the oil. So that's why I call it like riding a seesaw, because high and low results don't always correlate to high or low varnish, not in the same way that you would expect. So it's very important that you trend your results and look for changes in this trend, because if your results climb steadily, which is generally what's expected over the course of a few years, that would be expected. But if they suddenly leveled off, that would probably indicate to you that they're starting to plate out. If these values ever decreased on their own, that would definitely mean they're starting to plate out. So without any other interference by yourself, meaning that you've either sweetened the fluid or added some sort of varnish mitigation strategy to it, these results should slowly climb higher and higher and higher until they reach whatever their saturation point is. At that point, the results will level off and you probably see varnish would actually appear in your system. So just as a quick final thought here, one of the other things I like to point out when we interpret results is pitfalls, ways people commonly misinterpret the results. And since we're talking about MPC and UC, I'd like to share those pitfalls with you as the final say here. And that is that, for a lot of years, I found many people blamed the base oil, that changes to which API group stock was being used was an indication of whether or not you could expect or not expect to have higher varnish levels. That has since been disproven. There's been a few different studies done. One big one that was done by ExxonMobil showed that it didn't matter if it was group 1, group 2, didn't matter if it was high solvency or low solvency, you could get varnish conditions using any combination of whichever group with whichever type of solvency. It had nothing to do directly correlate with the base oil selection. So that's kind of a bit of a misnomer now. But the other thing you can see here that I'm pointing out is that I do point out it does not correlate. Right? It is not expected that your MPC and your UC values will necessarily correlate with some of the other tests like acid number or ruler or even RPVOT. Because again, these are all different measurements meant for a different purpose or coming at it from a different perspective. And therefore, you're not always going to see these results climb or fall together. So with that, I'll again go to the question slide here. So if there's any questions you'd like to throw up in the chat, I'll be happy to answer them. Otherwise, I do thank you for watching another live stream here. And if I see that there's no questions in the chat for about 30 seconds, I'll just end the stream. So with that, again, I thank you for watching.